Example 1. Determine whether the integral from 1 to infinity of open 1 over x closed dx is convergent or divergent. Solution. According to part A of definition 1, we have the integral from 1 to infinity of 1 over x dx equals the limit as t approaches infinity of the integral from 1 to t of 1 over x dx equals the limit as t approaches infinity of the natural log of the absolute value of x on the interval from 1 to t equals the limit as t approaches infinity of open the natural log of t minus the natural log of 1 close equals the limit as t approaches infinity. The natural log of t equals infinity. The limit does not exist as a finite number, and so the integral, the improper integral from 1 to infinity of 1 over x dx is divergent. Let's compare the result of example 1 with the example given at the beginning of this section. The integral from 1 to infinity of 1 over x squared dx converges. The integral from 1 to infinity of 1 over x dx diverges. Geometrically, this says that although the curves y equals 1 over x squared and y equals 1 over x look very similar for x greater than 0, the region under y equals 1 over x squared to the right of x equals 1 is the shaded region in figure 4 has finite area, whereas the corresponding region under y equals 1 over x in figure 5 has finite, has infinite area. Note that both 1 over x squared and 1 over x approach 0 as x approaches infinity, but 1 over x squared approaches 0 faster than 1 over x. The values of 1 over x don't decrease fast enough for its integral to have a finite value. Figure 4. Integral from 1 to infinity of open 1 over x squared close and dx converges. Figure 5. The integral from 1 to infinity of open 1 over x closed dx diverges. An infinite area versus a finite area. Example 2. Evaluate the integral from negative infinity to 0 of x times e to the power x dx. Solution. Using part B of definition 1, we have the integral from negative infinity to 0 of x times e to the power x dx equals the limit as t approaches negative infinity on the integral from t to 0 of x times e to the power x dx. We integrate by parts. With u equals x and dv equals ex dx. so that du equals dx and v equals e to the x. The integral from t to 0 of x times e to the power x dx equals x times e to the power x on the interval from t to 0 minus the integral from t to 0 of e to the power x dx equals negative t times e to the power t minus 1 plus e to the power t. Sidebar. In module 7.8 you can investigate visually and numerically whether several improper integrals are convergent or divergent. Back to the text. We know that e to the power t approaches 0 as t approaches infinity. And by L'Hopital's rule, we have the limit as t approaches negative infinity times t to the times t, restarting this line, the limit as t approaches negative infinity of t times e to the power t equals the limit as t approaches infinity of t over e to the power negative t equals the limit as t approaches infinity of 1 over negative e to the power negative t, which equals the limit as t approaches negative infinity of open negative e to the power t close equals 0. Therefore, the integral from negative infinity to 0 of x times e to the power x dx equals the limit as t approaches infinity as t approaches negative infinity of open negative t times e to the power t minus 1 plus e to the power t close equals negative 0 minus 1 plus 0 equals negative 1. Example 3. Evaluate the integral from negative infinity to infinity of 1 over 1 plus x squared dx. Solution. It's convenient to choose a equals 0 in definition 1c. The integral from negative infinity to infinity of 1 over 1 plus x squared dx equals the integral from negative infinity to 0 of 1 over 1 plus x squared dx plus the integral from 0 to infinity of 1 over 1 plus x squared dx. We must now evaluate the integrals on the right side separately. The integral from 0 to infinity of 1 over 1 plus x squared dx equals the limit as t approaches infinity of the integral from 0 to t of dx over 1 plus x squared equals the limit as t approaches infinity of the inverse tangent of x on the interval from 0 to t equals the limit as t approaches infinity of open the inverse tangent of t minus the inverse tangent of 0 close equals the limit as t approaches the infinity of the inverse tangent of t equals pi over 2. The integral from negative infinity to 0 of 1 over 1 plus x squared dx equals the limit as t approaches negative infinity of the integral from t to 0 of dx over 1 plus x squared equals the limit as t approaches negative infinity of the inverse tangent of x on the interval from t to 0. The limit as t approaches negative infinity of open the inverse tangent of 0 minus the inverse tangent of t close equals 0 minus open minus pi over 2 close equals pi over 2. Since both of these integrals are convergent, the given integral is convergent, and the integral from negative infinity to infinity of 1 over 1 plus x squared dx equals pi over 2 plus pi over 2 equals pi. Let's see sidebar figure 6. You have y equals 1 over 1 plus x squared, and the area equals pi. Back to the text. Since 1 over open 1 plus x squared close is greater than 0, the given improper integral can be interpreted as the area of the infinite region that lies under the curve y equals 1 over open 1 plus x squared close and above the x-axis. See figure 6.